Hello, Anchal. Good evening. Okay, we'll wait for a while for others to join. How's it going? Are you reading from your book? Okay, so you have Pradeep, right? Okay. I do have the copy of Pradeep book. So in case of any doubt, you can just let me know the page number so that I can see the doubt, right? We'll just wait for 2 to 3 minutes more. Did you read this dimension analysis and stuff that we studied last class? Hmm. Is it clear? Mhm. Okay. We'll see a little bit more in like in a bit organized manner, so that we can learn that how to write an exam. Hmm. Hello, Ashwin. How are you? We'll just wait for 2 minutes for Rohini to come. Otherwise, we'll start. Oh, okay. If that is the case, then let us start. Not to waste any more time. Yeah. Okay. 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 Fine. 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 Okay. So we are going to start then. Okay. Um, we'll just revise a little bit what we learned in the last class. We were after solving few problems for vectors, we started with dimension formulas, right? So in the last class, we already discussed what are dimension formulas. So that we discussed that every physical quantity can be expressed in seven base quantities. As we discussed that physical quantities are of two types, base quantities and derived quantities. So every physical quantity can be expressed in seven base dimensions or seven base physical quantities, right? We took the example of, say, in the last class, we can take the example of area. If I take the example of area, which is actually length into breadth, say of rectangle, right? So it will be actually length into length square. Yeah, so its dimension will be length square. Again, we are expressing this quantity in form of base quantities. Now we know that length is a base quantity. So any physical quantity can be expressed in its base quantities. Like if we take the example of acceleration, then we can write it as m0 L t to the power minus 2. Yeah. So this is how we can represent any quantity in terms of base quantity. Sometimes in exam, it is basically, sometimes it is written that what is principle of homogeneity, right? Though we discussed in the last class, but let us write it in a formal manner. What is the principle of homogeneity? Homogeneity is, sometimes they may ask you to let that prove that principle of homogeneity is applicable in this equation. So you must be knowing that what is the principle of homogeneity. This is basically of dimension, homogeneity of dimensions, of course, right? So what is the principle of homogeneity? As I told you in the last class, some equation, it may be a combination of two or more than two terms. For example, let us take the example of our equation of motion. If I say v is equal to u plus at, yeah, that is the equation of motion that we have already studied in our ninth class. Now, principle of homogeneity means that every term of an equation, be it the right hand side or be it the left hand side or the right hand side, every term should have the same dimension. This is what we explain by principle of homogeneity. That is, it should be homogeneous. Every term should be homogeneous in terms of its dimension, be it the left hand side or the right hand side. any term of the left hand side or the right hand side. So every term shall be homogeneous, that is its dimension should be same. So we can see here its dimension is of the left hand side, its dimension is L t to the power minus 1, yeah, velocity meter per second. Then this is initial velocity, again same dimension, L t to the power minus 1 plus. Okay, so now what are the dimensions of acceleration? Meter per second square into, we all multiplying by time, so this will be meter per second again, so again it will come out to be lt to the power minus 1. Obviously you have never heard that we can add 5 meters into 10 seconds. No, we cannot add 5 meter to into 10 seconds. So whenever we add or subtract any equation or any quantity, it has to be with same dimensions, right? We cannot add or subtract two quantities with different dimensions, though we can multiply any quantity. Yeah. So that is how, this is what we call the principle of homogeneity. That is, when a physical quantity consists of a number of terms, then each of the term should be of same dimension, right? Okay. Now this much is clear, I guess. Now let us see an example of it, right? Write down the example. Oh, hello Rohini. How are you? Rohini, can you hear me? Hello, Rohini, can you hear me? Uh, okay, guys, we'll continue with the example. So, for example, if I have, this is the example of principle of homogeneity only. Let us say P represents our power. P represents a power. Then P is equal to x square minus B divided by A into T. Yeah, P is equal to x square minus B divided by AT. See, x represents the distance, x represents distance, T represents time. Okay, A and B are constant. A and B represents constant. Yeah, and P represents power. Now, what you need to do, you need to find the dimensions of A and B. You need to find the dimensions of A and B, right? A and B. You have to apply the principle of homogeneity. Find the dimensions of A and B. Shall I give a hint? Just take AT on the left hand side so that you can apply the principle of homogeneity. That is, left hand side is equal to dimensions of each term on the right hand side. Solve it ASAP. Okay, Rohini, I'll just explain you what is this principle of homogeneity. Meanwhile, others solve the problem. Principle of homogeneity that we already discussed in the last class. Principle of homogeneity states that uh, every physical quantity, it may consist of a number of terms. For example, we wrote this equation. Okay, so every physical quantity may consist of a number of terms, and each of these terms must be of same dimension, right? Every term on the left hand side and every term on the right hand side, it should be of same dimension. That is, V, U is another term, AT is another term. All these should be having same dimensions, which is what we call principle of homogeneity of dimensions. That is, there should be homogeneity in the dimensions of each and every term in an equation. Yeah. So here we discuss that dimensions of V, which is velocity, meter per second, L t to the power minus 1, U, L t to the power minus 1, acceleration into time, meter per second square into second. So meter per second, again L t to the power minus 1. So we can see that this equation is valid as their dimensions are equal. Okay. So you have to solve this question. That is, you need to find the dimensions of A and B. Guys, if any one of you needs audio access at any time, just let me know. I'll give you the audio access, right? You don't need to write your doubts always. Sometimes it is difficult to express the doubts in written manner. Done? Shall I solve it? Okay, let us solve it. A, hmm, aren't you getting anything for T? M to the power minus 1. Yes, correct. Anchal, you are correct. Ashwin, it's M to the power minus 1, T to the power 2. Anchal, good. Correct. And what about B? Mm, B, T to the power 2. Is it T or L? Ah, L to the power 2. Very good. Perfect. Ashwin, are you getting something for B? Rohini? Okay, let us solve it. See, we can write it as P into AT is equal to x square minus B. Yeah. So, as we told that first of all we'll approach by this term. Why? Because every term should be having same dimensions, and as we can see, there is some unknown in this term and there is some unknown in this term, but we know the dimensions of this term. So we can see dimensions of this term is L to the power 2. Yeah, L to the power 2. Now if we are subtracting these two terms, then these two must be having the same dimensions. So dimensions of B must also be equal to L to the power 2. Is it clear? Okay. Then what about dimension of power? We already know that power is equal to what? Rate of work done, that is work done per unit time. And work done is what? Force into distance by time. And how can we write the dimension of force? Force dimension is m L, because force is mass into acceleration, so L to the power 1 T to the power minus 2 into distance is again L divided by this will be T. Now you can see if we multiply A into T, right? Let us say multiply first T, then this will be what? Again dimension of T, so this will cancel out. So we can write dimension of p into t, that will be m l to the power 2 t to the power minus 2 into dimension of a. Now this must be equal to what? Dimension of any of these two terms, which is equal to L square. Yeah. So then we can write dimension of A. So we will divide it, with this dimension of A will be what? We will divide L square by this m to the power 1, L to the power 2 and t to the power minus 2. So we can write here A will be dimension of A will be equal to L to the power 2 divided by m L to the power 2 t to the power minus 2. So it can be written as m to the power minus 1 L to the power 0 t to the power 2. Ashwin, did you get your mistake? Okay, Rohini, is it clear to you? Okay, how we get B? See, I explained in the principle of homogeneity that every term should be having the same dimension. You obviously, for example, you cannot add, for example, if I say what will be 5 meter plus 10 seconds, you cannot add them because they are not the same physical quantities, or their dimension formula is not same. So only those terms can be added or subtracted which are having the same dimensions, which is what we said in the principle of homogeneity, that is every term should be having the same dimensions, right? Then in this case we rearrange this formula, which is PAT is equal to x square minus p, in order to have the same dimensions, right? Okay, so it means if x square minus b, if we are subtracting these two terms and this formula is valid, which is given, then both of them must be having same dimensions. So if the dimension of x and x was our distance, so this term is having the dimension of L square, right? Then what will be the dimension of this? It also has to be L square, because you can subtract only same quantities, right? So that's why if this term is having dimension L square, then B will also have the L square dimension. Is it clear? This is already in the RHS, or we are talking about LHS. Every term, every single term will have the same dimension. See, this term, and this term, they all should have the same dimension. Then only an equation will be valid. For example, as we took the example of this v is equal to u plus at, every single term should have the same dimension. You can see meter per second. This will also be meter per second. Acceleration into time, again meter per second. So for a term to add or subtract, it should have the same dimension. Yeah, not it shouldn't be a case that this dimension formula of this term shall be equal to sum of these two. No, sum of dimensions of these two. No. Every term shall have the same dimension. Then only you can add one quantity into the similar quantity. Na? You cannot add distance into time. You cannot add time into acceleration. You can multiply them, but cannot add or subtract. Right? So that's why every single term should have same dimension. Clear? Okay. Shall we go ahead? Okay. Okay. Now let us discuss next. Now we are going to discuss what are the utilization of this dimension analysis. So dimension analysis, basically we have already discussed what is dimension analysis. That is the process of analyzing a physical problem with the help of a dimensional equation. Now, where do we use this dimension analysis? First of all, first application is to check the correctness of a physical equation. To check the correctness of a physical equation. We can check the correctness of a physical equation by comparing their dimensions. Let us say, take this example, v square is equal to u square plus 2as. Can you check the dimensions? For this equation to be correct, every term every term should have the same dimension. Every single term should have the same dimension. Can we find the dimension? You can see every term is having the same dimension. For example, when this is velocity square, this will be what? L to the power 2 t to the power minus 2, right? Similarly, this is also velocity square, though it is initial velocity, but doesn't make a difference in the dimension, right? So this will be L to the power 2 t to the power minus 2. Now this one, acceleration into displacement. Acceleration is what? L t to the power minus 2. And what is the dimension of displacement? Again L. So this will become L to the power 2 t to the power minus 2. So this is the first application, that is to check the correctness of a physical equation. So he may ask you in the exam that whether this equation is correct or not. So you have to compare the dimensions, or you have to analyze the dimensions of each and every term. Is it clear? Okay. So keep it writing on your notebook. Okay. Now next, what is the second application? Second application is we can derive relation between different physical quantities. Second is to derive relation between different physical quantities. Yeah, we can derive relation between different physical quantities. How do we do that? For example, guys, what is kinetic energy? Kinetic energy is 1 by 2 mv square. We have already studied in our 9th class. Okay. But instead of giving this kinetic energy, let us say I am not given this formula in the first go. Yeah. I need to derive this formula. Let us say I am not given this formula. Yeah. I need to derive this formula. That is, I don't know whether kinetic energy is equal to mass or is equal to mass ka square. I don't know whether this is equal to velocity or it is equal to velocity ka square. So let us assume that this energy, kinetic energy, obviously I will find out that kinetic energy is dependent on mass. That is, it is proportional to mass. By what power I do not know. And it is proportional to velocity. By what power I do not know. So I put A and B, which are unknowns. Now, how will I know that it is dependent on mass? That we will do by experiment. This is experimental fact. That is, kinetic energy is depending on mass. By what power I don't know. And this is also depending on velocity. By what power? That I also don't know. Now, how do I find the value of this A and B? Then we can see what will be the dimensional formula of energy. Dimensional formula of energy. Energy is basically work done, which is force into distance. Now, dimensional formula of force, ml t to the power minus 2, and work done will be force into displacement, ml2 t to the power minus 2. Now, this dimensional formula must be equal to dimensional formula of these two by multiplying these two. Let us say, what will be dimensional formula of mass? We know that it will be m to the power a. Then, what will be the dimension formula of this? It will be L t to the power minus 1 raised to the power b. So, it can be written as m to the power a, L to the power b, t to the power minus b. Is it clear? So, we can say, and this dimension formula must be equal to this one. So, we can find the values of a and b. What are the values of a and b? Tell me, yes, sir. A is equal to 1 and b is equal to 2. Very good, right? So we can directly compare these values. A is equal to 1, b is equal to 2. So this is the second application of the dimension formula, that is to derive a relation between physical quantities, right? So here we found out that this kinetic energy is proportional to mass to the power 1, v to the power 2. Obviously we know that this is half mv square. Yeah. So this is proportional to mv square. So this is how we can use this to find this value. Any other doubt? Any question in this? Is it clear? All of you? Okay, good. Okay, then next. Then let us see the third application, which we also solved one problem on that in the last class. That is to convert one system of unit into other system of unit. Write down the point C. We use this third application to conversion of one system of unit one system of unit into other system of units. One system of units into other system of units. What do we mean by that? Like in the last class, we converted 1 Newton into dynes. Yeah, that dynes was the CGS unit, Newton was the SI unit. So if we have to convert such quantities like that, then guys, how do we write it? We represented this like this one, though we did in the last class also, but just how do we write in the paper? This is equal to N2 U2. Yeah, N1 is like that is unknown, that is known. That is, for example, if you need to convert 1 Newton, then N1 will be having the value of 1. That is known numerical value. Known numerical value. Yeah. U1 is what? U1 is the given system. U1 is the given system of unit. Given system of unit. For example, 1 Newton. That is a Newton is a given system of unit. Yeah. Then N2 is unknown. Unknown numerical value. N2 is unknown numerical value. Is it clear? Unknown numerical value. Yeah. Then similarly, U2 is required system of unit. Required system of unit. That is, if we have to convert into CGS system, then length will be in centimeter, mass will be in gram, and time will be in second again. Now, if I apply this to our 1 Newton and 1 Newton into dynes, right? How do we do it? 1 Newton. So N1 is 1 into. What is the dimension formula for this? For force, Newton is mL t to the power minus 2. Yeah. Okay. Then this is equal to N2 that we need to find out. Then again this is write down this M1 L1 T1. Why? Because we are using different system of units. So this will be L2 T to the power. Okay, dimensions will remain same for force. Yeah, be it in newtons, be it in dynes, dimensions will remain same. Okay, now we will write this as follows. So it will be N1 is equal to 1, that is M1 L1 T1 to the power minus 2 is equal to N2 M2 L2 T to the power minus 2. Yeah. Now what is M1? Now this can be written as M1 by M2, L1 by L2, T1 by T2 to the power minus 2. Yeah. So that will be equal to N2. Clear? Now M1 was our given system unit. What was that? 1 kg. In what system we have to convert? Gram. So this is 1 gram. 1. Then this is what given system is 1 meter. We have to convert in centimeter. So this is this thing. Then this is 1 second and 1 second. CGS or SI both have same unit of time. So from here we can see is equal to N2. So we can find N2 is equal to, this will be 1000 into 100, right? So we can see 10 to the power 5 dyne. Guys, any doubt? This is just a formal method of writing it. Formal method of writing it. Is it clear? Okay. Yeah. So we already did it in the last class. You may note it down. Then next, solve the question. You have to convert 1 joule into erg. Erg is the CGS unit of energy. Yeah. Joule is, as you already know, SI unit of energy. So convert this into erg. CGS again, length will be in centimeter, mass will be in gram, time will be in second only. So convert 1 joule into erg. Guys, you have to do in the same manner that I have showed you how to solve. Yeah, because this is how we will write in exam. So no variation. Solve it, sir. Oh. Yes, perfect. Hmm. Good. Okay, good. Good, all of you. Let me just show you in case so that you can match. We will write N1 U1 is equal to N2 U2. N1 is given 1, which is 1 joule. That is M1 um, L1 square T1 to the power minus 2 is equal to N2. That we need to find out. This is M2 L2. Unit will remain same, minus 2. So N2 will be equal to 1 kg by 1 gram into 1 meter by 1 centimeter square 1 second by 1 second. So it won't make a difference. So we can write it as 1000 into this will be 100 ka square and 10,000 into 1. So we can write 1 joule is equal to 10 to the power 7 Earth. Yeah, as we calculated the value of N2. So 1 joule, because N1 U1, which is 1 joule, N1 U1, right, is equal to N2, which is 10 to the power 7 U2 Earth. Any confusion? Okay, then then what are the limitations of this dimension formula? They're like sometimes it may be asked in the simple school exams. Though this is none of our concern in our IIT preparation, but still, what are the limitations of this one dimension formula? As we have seen the three applications of this dimension formula. So first limitation is it does not give us any info about dimensionless constant. For example, in when we calculated kinetic energy, which was equal to half mv square, we could calculate only that when it is m into v square. We could not see that what is the constant that may need to get multiplied. Yeah, so it does not give any information about the dimensionless constants or any number. Then it also fails to derive the exact form of physical relation. Ashwin, are you having some doubt? Rohini, what? Okay. Am I clear now? Okay. So I was saying, dimension analysis does not give us any information about the constant or the pure number. As we solved the example for kinetic energy, in which we could deduce only that kinetic energy is proportional to m to the power 1, v to the power 2. We could not find that what constant we have to multiply. As we know, kinetic energy is half mv square, right? So it does not give us any information about the dimensionless constants. Then it also fails to derive the exact form of physical relation, which is the same thing. That is, since we cannot determine the dimensionless constant or pure number, so it fails to derive the exact form of physical relation. That's why we cannot use it for deriving relations. Yeah. Then it cannot be used for trigonometric and exponential functions. Yeah, it cannot be used for trigonometric functions, because there also it will fail, because there are no dimensions of trigonometric functions. Yeah, though we know that physical quantities are also in terms of angle. For example, angular displacement, in which displacement is in form of angle. Yeah, so angle is in radian, which does not have any unit. Yeah, so we can say it cannot be used for the relations which are involving trigonometric or exponential functions. So and also, as we check the correctness of an equation, yeah, correctness of an equation can be checked by dimension formula, but we can check the correctness, but only dimensional correctness, but we cannot check the overall correctness. For example, v is equal to u plus at. We check the dimensions, so we can check the dimensional correctness, but not overall. What do we mean by not overall? For example, if I say v is equal to u plus at, now whether I write v is equal to u plus 1 by 2at, I cannot determine by dimension analysis, that is this 1 by 2 should be here or not, right? This cannot be determined by the dimensional analysis, right? So we can check the dimensional correctness but not the overall correctness of the equation. So this is what these are the limitations of the dimensional formula. Any confusion? Okay, then okay, we will solve few problems later. If at the end we have time, then we are going to solve some problems, right? Now let us jump to the error chapters. What are errors and how do we use it? We will be very short and crisp again. Then first of all, before going into errors, let us define what is the accuracy and what is the precision. Then first of all, write down what is precision. We just need to understand its meaning. Definition you can learn from your book. Okay, I'll type precision. Precision, you may also note it down. Precision is the limit to which a quantity is measured. Precision is the limit to which a quantity is measured. We can never obtain a result more precise than the limit of measuring device. Then comes the accuracy. It signifies the what I should say, degree of closeness between measured value and true value of a physical quantity. Yeah, so this is what we say, accuracy and precision. Just note it down, then I'll explain. Okay, just wait for a second. Ashwin, answer done? Okay. Ashwin, are you done? Okay. Now let us see what is precision. See, we are saying that precision is the limit to which a quantity can be measured. It is the limit to which a quantity can be measured, right? We can never obtain a result more precise than the limit of the measuring units. For example, we are measuring a quantity. Let us say you need to measure this length. Obviously, you are going to scale. Now we have seen our 15 centimeter scale. Then what is the minimum spacing that we can measure? In that you must have seen that it is divided into certain sections. Then you have seen that is first centimeter, second centimeter, third centimeter, first centimeter, second centimeter, third centimeter, and so on up to 15 centimeter, right? Yes, very good. So 1 centimeter is divided into 10 parts, that is 10 millimeters, right? So we can, at best we can measure is 0.1 centimeter or 1 millimeter. This is a limit. If we have a length which is say 0.5 mm, we won't be able to measure by this scale, because at best our least, this is what we call also least count. This is also the least count of the scale, that is you can measure at best up to 1 mm. A length smaller than that you cannot measure that, right? So precision is up to what limit you can measure. More the limit you can measure, more precise your equipment or your device is. For example, if I say 2.3 2.3 centimeter. When I say 2.36 centimeter, then this quantity is more precise. This quantity is more precise because I can measure up to 2 digits after the decimal. So I can measure up to, see here this part is, okay, let me explain what are these different digits. See, this part is known as reliable digit. Reliable, because obviously this we will be sure that this is reliable or sure. Yeah, this is a sure part of this. This is unreliable. Unreliable. For example, we measured a distance by our scale, right? And with our scale, we measured that it is 2.3 centimeter. That is 2 centimeter plus 3 millimeter, right? This is what we mean. Now, this 0.3, this 3 digit, that this is unreliable or unsure digit. Why so? Because we are measuring the length as 2.3 centimeter. It means it is up to 3 mm, but we are not sure about it because our length can be 0.35 millimeter, but since our scale cannot measure below 1 millimeter, so we are stuck up to here only, right? So 2 becomes a reliable digit or sure digit, and this last digit becomes a unreliable digit, right? So similarly, if I have 2.36, then 2 and 3 both are sure digits or reliable digits, right? But last one becomes unreliable digit. Why? Again, the reason being, since this your last is, as we are measuring the distance to be 2.36 centimeter, it may be 2.368 centimeter, but since our least count is 0.1 millimeter, so we cannot measure beyond that, right? So whatever, up to whatever digit you measure, always the last digit will remain unreliable. But here we are discussing about precision, so we can say this quantity is more precise because it is giving more information, right? Its least count is even less, so that's why this quantity is more precise. Is it clear? What is precision? Okay, then let us come to accuracy. What is accuracy? It signifies the degree of closeness between the measured value and the true value of a physical quantity. For example, I am having time period of a clock, right? Say clock or anything. Let us say time period is 2.4 seconds, right? This is true value, which we know, that is, this is at the actual time period. Now, some student does some experiment and he measures the value of this time period. Now he measures that value is, say he measures the value 2.3 second, right? So if he measures the value 2.3 second, and if one other student measures the value 2.2 second, then we will say, by this quantity 2.3 second is more accurate. This quantity is more accurate. Why? Because this is more close to the true value. So accuracy is the degree of closeness. That is how close the measured value is, to true value, right? That is, the measured value is how much it is close to the true value. So more closer it is, more accurate it is. Now, one student measures this value, say 2.26 seconds, right? This is student 1, this is student 2. Yeah? So one student measures 2.26 seconds, other student measures 2.3 seconds. Then we will say this quantity is more precise because it is giving more information. That is, its least count is even less. Yeah, but this quantity which the second students measure, this is more accurate. Why? Because this is more closer to the true value as compared to this one, as compared to student 1. So we will say this is your more precise and this will be your more accurate. Is it understood? Okay, great. So did you note this definitions and the example? Note it down, yes sir. With examples. Okay, great. Now let us discuss about what are significant digits. Yeah, significant digits. So I guess you already might have studied about this significant digit. Okay. Now let us study what are these significant digits. Okay. So what are these significant digits? Significant digits are basically whatever any quantity if we are measuring. Yeah. As I told you, for example, if we measure the length as 2.468 centimeter. Yeah. We need to find what are the significant digits. That is how many digits are significant for the quantity to be measured accurately. Yeah. So that's why we will determine significant digit in every quantity, in every number. Yeah. So that is what we are trying to find. Key, what are the number of significant digits? So what are significant digits? That number of digits in a measurement. Yeah. About which we are absolutely sure, plus the last one will be uncertain digits. So all these digits, the number of digits in a measurement about which we are sure, and plus one digit which is uncertain. That is the reason I told you. For example, this digit is uncertain digit because we don't know. Maybe our length may be for 2.4682, since our least count is up to this only. So that's why we are missing. So the last digit is always uh, unreliable one, right? So what are the significant digits? The total number of digits. We will be learning about different rules. What are the digits that we need to count to calculate the significant digits in a quantity? Yeah. So significant digits are the number of digits in a measurement. One is the sure digits. These three are the sure digits. This is the uncertain digits. So you can write it here. So this is your sure digits or the sure numbers, or this is your unreliable digits. Yeah. Unreliable digit. So okay, is it done? Now let us study some rules, that is how to find what are the rules for counting these significant numbers. What are the rules to count these significant numbers? Okay, now we are going for the rules. Okay, so note down rules to determine significant figures. In a physical quantity, how do we determine the significant figure? I already typed it. Okay, so we will just discuss and then we will write one example for everything. Okay, so you need to write all these rules because these are very important. Significant digits, definitely you are going to face a question in your school exam. Okay, okay, let's discuss. So what is this first rule? We are saying all non-zero digits are significant figures. Doesn't matter what is the kind of number, whatever it is, any non-zero digit, it will always be a significant digit. For example, let us take the example of 22.68 centimeter. So in this case, we can say all these are non-zero numbers. So number of significant digits will be 4. So number of significant digits are 4. All non-zero digits are significant digits. Understood? First part. Okay, noted, and keep on noting it down. Then second part, all zeros between two non-zero significant numbers are always all zeros between two non-zero digits are always significant figures. And in this case, decimal point will not matter. That is what is the position of the decimal point, right? All zeros, because see, only this zero will be going to make it trouble. That is whether it is to be counted or not. So we will be very specific about these zeros. So if we are facing any zero between two non-zero digits, then this zero will always be a significant figure, right? So and one is this zero and other is the decimal point. These two things make most of the trouble, right? So in this case we will say all zeros between two non-zero digits are significant figures, irrespective of the position of decimal point. Does not matter where the decimal point is. If, for example, let me take the example, if this is say 2090.03, we need not to confuse that is whether this is after decimal point or before the decimal point. since all the zeros are between two non-zero digits, so all zeros will also be counted as significant figures. So we can say significant figures in this case are 6. Done? So all zeros between two significant figures, between two non-zero digits, are always significant figures. Okay, then let us see the third part. So when there is no decimal point, 0 at the end are meaningless and they are not counted in the significant figure. That is, when there is no decimal point. For example, if I take the example of say 3600, yeah, so we can say this 3600, these two zeros are non-significant. That is, it does not have any significance. Number of significant digits here will be 2. Then let us take another example. If there is no decimal point, mind it, if there is no decimal point, let us say this, we take the example as 143000. Again, significant digits will be 3. So, or when there is no decimal point, zeros at the end are meaningless and they will not be counted in the significant figures. These are just rules. Similarly, because why is that? For example, we can also write it as 1.43 into 10 to the power 3. Yeah. So again, we can see significant digits are 3. Yeah. So we can write it as 143,000 or 1.43 into 10 to the power 3. Yeah. So in both cases, significant digits remain same. That is 3. So it does not matter how do you represent it. Yeah. Understood? Third point. Okay. Let me know of any confusion. Okay. Then let us discuss our next point. So next point is, whenever there is a decimal point, zeros at the end are significant. That is, zeros on the right hand side of the decimal and to the right of the non-zero digit are also significant. For example, if I say 0, let us say it is 36.00, then we will say number of significant digits are 4. That is, whenever there is a decimal point, zeros at the end are significant. Why they are significant, you need to understand. Because if we are writing it, we cannot just write, if we have measurement as 36, if we write now 36.0, it is wrong. Why? Because if your measurement is only 36, it means your instrument could measure only up to this least count. But if you are writing up to 36.00, it means you have measured these two digits and these two digits came out to be 0. Yeah. So that's why we will write these significant figures as 4. So that's why these two zeros, these are very important because these are showing the accuracy of this, precision of this, right? So that's why this will be counted in the significant figures. That is, zeros on the right hand side of the decimal and to the right hand side of the non-zero digit is also taken as significant. For example, if I say 0.3600, again, as I told you, this 00 also represent the accuracy or the precision, right? This 00 also represent the precision. So we will say zeros on the right side of the decimal or to the right side of the non-zero digit. That is, after the decimal to the right hand side of the non-zero digit. This will also be counted as 4. Clear? All of you clear? If any doubt, let me know. Is it clear? Okay, just keep on noting down these examples also. Yeah. Then let us come to next point. Point number 5. So whenever there is a decimal point, initial zeros after the decimal point are not significant. That is, zeros on the left of the non-zero but on the right hand side of the decimal are not significant. Let us see the example of this one. Say if this is 0034, then guys, these three zeros are not significant. So whenever there is a decimal point, initial zeros after decimal point, mind it, in this case these zeros were at the end and they were significant, while in this case initial zeros after decimal point are not significant. that is 0 on the left hand side of the non-zero but on the right hand side of the decimal. Left hand side of the non-zero and but right hand side of the decimal, they are non-significant. So in this case our significant digits will be, sorry, not 3, 2. Significant digits will be 2. Done. These are various rules. Okay. Okay, then let's come to sixth rule. 0 put on the left hand side of a decimal point for a number less than 0 is never significant. Guys, this is just convention. That is when you write a measurement, say 0.2 centimeter. This 0 is a convention. We can write it as 0.2 centimeter, but just conventionally we write a 0 in front of it, right? So we are saying a 0 put on the left hand side of the decimal point. This decimal point on the left hand side. This 0 will never be a significant digit, right? So this 0 will always remain a non-significant figure. So in this case we can say significant figure is only 1. Significant figure is only 1. So let's take some more example. 0.2300 centimeter. In this case significant figures are 4. If I say 0.0023 centimeter, significant figures 2. Understood? Done, all of you? Okay. This you might have studied from your textbook, so I guess there shouldn't be much of a problem. Then, guys, this is just the basic thing. Just since we are discussing all this, so let us not get this also. How do we round off the digits? Yeah, rounding off. You already know all this. For example, if I have 9.786, how do we round off this number? We know that if the last digit is greater than 5, then we increase this number by 1. So this will be 9 point. Which one, beta? This 0.0023? No, this will be 2. Because these three zeros are non-significant. Only these two will be significant. We told you. For example, we took the example of this 0.0034. Decimal point, initial zeros after the decimal point, they are non-significant. And or we can say zeros on the left hand side of the non-zero digit, left hand side of the non-zero digit, and the right hand side of the decimal. They are always non-significant. So this is 0.0023, so it will be 2. Done? Okay, so we were talking about rounding it off. So it will be 9.786. We can write it as 9.79. And if is 9.784, that is if the last digit is less than 5, then we will write it as it is, that is 9.78. Then if the last digit is equal to 5, what happens if the last digit is equal to 5? For example, 9.765. Yeah. So if this is an even number, then it will remain as it is, that is 9.76. But if it is a odd number, then it will be increased by 1. So it will be like this. Understood? So that is how we change or we round off these values. Done? Yeah, this you might be already knowing that. Okay. So we'll go to the next part. Okay. Then guys, we are going to discuss now what are the rules of arithmetic operations with significant figures. That is, when we are, for example, we need to add, just write down rules for arithmetic operation with significant figures. What are these various rules for arithmetic operations with significant figures? That is, how do we add and subtract and multiply and divide, etc., etc. For example, first is addition or subtraction. Let us say I am given add, just note it down, 3.2123 plus 40.5 plus 2.0123. If you need to add, you can see all are having different significant digits. This is having 4 significant digits, this is having 3, this is having 5. You can see 0 between two non-zero digits is always significant. 0 between two non-zero digits significant. So all these are having different significant figures. How do we add them? We can see that if we, by our basic mathematics, if we add, it will come out to be 45.7253. Is it? Yeah. So, but how will I quote this addition? If one asks me the answer, then I will say it to be 45.7. Now, why is that? What is the rule? Because whenever I add or subtract, then I will always quote the final answer which is having the precision of the least precise value of any single term. In this case, we can see this term is having the least significant digits. So my answer should also be having the least significant figure, should be having the least significant figure which is of any individual term in the addition or subtraction. That is, I cannot represent it as 45.72. Then it means this quantity was not precise enough, right? So I cannot represent this quantity with more than 3 significant digits. So my final answer should reduce to the least number of significant digits of any term which is having that least number. Is it clear? Okay. Then similarly, if I subtract, for example, 53.3 minus 53.312, what it will come out to be negative of 0.012, right? Then, but what should be my answer? Tell me, what should be my answer? Not 0.01. Acha, yes, this is valid doubt. See, answer should be 0.0, not 0.01. Why? Because you are taking the logic that it should be having it should be having the least significant digits whatever is given in the term, right? So this term is having least significant figure which is 3. So answer should also be having significant digits. No, why? In that is true, but we can see after decimal we are having precision only up to one value. So though we may need to represent 3 significant digits, but since we cannot represent by, because this term is having only one digit precision after the decimal point. So this will be 0.0. We cannot add one more digit after the decimal point, right? So though this is 2 significant digits, but we cannot help it, right? It shouldn't be the case that it exceeds the number of significant digits present in any term, but certainly it can be less or it can be equal, but it cannot be more. It can be less in case when you are having when you have to equate the precision after the decimal point. Yeah, so that's why I took this example. Yes. This will be one only. Yes. This is having only one significant digit. Right. Correct. Thank you. But you understand the point? That is, after decimal, we must be having only one digit because this term is having only one digit, right? So number of significant digits, it should be equal to the least term. It may be less. Hello, Rohini, can you hear me? I guess you are not able to hear. Rohini? So, is it understood? Am I clear? Yeah. So, basic rule is uh, these digits should be equal, but the precision after the decimal point that must hold. That shouldn't be more precise, right? Okay. Then let us come to multiplication and division. Rohini, can you hear me now? Okay, she's offline. Now let us discuss the next part, which is multiplication and division of the significant figures. Okay. Um, Let us discuss multiplication. For example, if I multiply to say 4.08 into 16, this comes out to be 65.28. Now, that what will be the final answer that I will quote? Ah, perfect. So I will quote only 65 because this number is having two significant digits, so I must not exceed this value. Is it clear? Then let us say the case of division. For example, if I divide 6300 by 11.97, it comes out to be 5.5263157, etc., etc. I already calculated this over there. So this, now if I need to quote the result, what I will quote? 526.3. Okay. Can you tell me what are the significant digits in this one? Yes, 2. But you are reducing it to 4. No. Though we need to apply our rules, but we also need to apply some logic and common sense. Hi, how? See, obviously, when we divide 6300 by 12, we cannot get 52, right? But we can see here the significant digits are only 2. So we could try to reduce it to 2 significant digits, but we can see that these first 3, they are as important, they are very important, right? Unlike this part, right? So we can neglect this part only. So we will write it as 5 uh, to 6. Just hear me out, because I'll just tell you after this. So if it is 5 to 6, now since 5 to 6, this is not fair also. 5 to 6, we have only uh, two significant digits. Now you can see this 6 number is what? Greater than 6 number is greater than 5, so I can reduce it to 530. Yes, 530. Now again, if it is 530, it satisfies my both problems. One is division, it sounds as good as it should be, right? Number two, it is having only two significant digits. It is having two significant digits. Is it clear? Yeah, this is a little bit vague, but this is how it is. I can't help it. Yeah. See, one again, I'm repeating it. Rohini, can you hear me now? Okay, I'll just explain you in quick manner. We were talking about how do we multiply and divide significant figures. For example, we took this example 4.08 into 16, and this comes out to be 60.5.28, but we will write it as only 65. Why? Because least significant digit is 2, so we'll write as 65 only. In this case, we were discussing division, that is 6300 divided by 11.97, that comes out to be 526.31578. Now we can see least significant digit is this number 2, but obviously we cannot reduce it to 52, because obviously if you divide 6300 by 12, approximately 12, then it won't be in 2 digits, it has to be in 3 digits. So do we write it 526? No, since we have to reduce it to two significant digits only. So since 6 is greater than 5, so approximated it to 530. So again, this solves our both problems. One is it reduces to two significant digits, other is uh, it makes the sense that it should be in 3 digits. So this is approximate values. This is how we reduce it into significant digits. Yes, Rohini, any doubt? Ah, yes. Let me explain the subtraction part. See, in this subtraction, 53.3 minus 53.312, this subtraction came out to be 0.012. Now, we are having here significant digits as 3. Okay, then if these are 3, then shall it be 0.01? Obviously not. Why? Because along with the number of least significant digits, we also have to take care that what is the maximum precision that we can quote in the answer. In this case, maximum precision in our any of the term least precision was only one digit after decimal. So we can quote only one digit after decimal. We cannot show more precision than that because this quantity or this term was least precise. That is, it was having only one digit after decimal point. So this will reduce to zero point 0. That is not 0.01, it will reduce to 0.0, though this is one significant figure, but above that this rule must hold, that is after decimal it must be having the same precision, right? So this is having the same precision after decimal, so it answer will be 0.0. Clear? Rohini, clear? Okay. So am I clear with all of this? Okay. Mm, are you having the calculators with you or your mobile phones so that I can give you one problem? Because okay, okay, okay. So just solve one problem. It is actually you can use a calculator in your mobile or actual calculator, because we just need to think in terms of significant figures. Calculation we can do in exams also. So let us say if length is 4.234, my breadth is say 1.005 meter, uh, thickness, or you can say height, is 2.01 centimeter. Okay, then what will be the area? What will be area? So what do you have to do? You have to multiply and reduce in the significant figure. Just write down the formula of the area. That will be twice of length into width plus width into thickness or height plus length into thickness. Okay, so use the calculator and solve for the final answer. Guys, mind it, this length is in meter. Okay, width is also in meter, but this thickness is in centimeters. So first convert this in centimeters. So it will be less than 0. That you need to take care of. You have to calculate the area in meter square. Just use, we just need to show how many significant digits that we will show. Uh, huh? 29.57. What are you getting? Bachai, have you converted this 2.01 centimeter into meter? Anchal, you are perfect. 8.72. Very good. Rohini, just check the calculation. It will be 8.72. Uh, right? You are getting 8.52. Though you have reduced to the significant figures, very good. Yeah, you have reduced to the significant figures correctly. Just there might be some calculation problem, but this is good. Very good. Ashwin, uh, have you reduced this thickness into meters? I guess not. That's why you are getting such a large value. Ah, that's what I told you, na? Thickness. This is in centimeter, bacha. You have to convert into meters. Yeah, convert into meters. That is, it will be what 0.0201 meter. And you can see this does not make the difference in number of significant digits. Here we can see significant digits are 3. Here also significant digits are 3. Yeah. So actually your area must be coming out 8.720947 I guess this must be the final value that we must be getting. And we will reduce it to 3 significant figures. Yeah, because we can see we have least number of significant figures. Here is 3. As you can see, here we have 4 significant figures. Here also we have 4 significant figures, but here we have 3 significant figures. So our answer cannot be more than 3 significant figures. So it will be 8.72 meters square. Acha, if it would have been say 727, then what we would have written? 8.73 meters square. Understood, everyone? Rohini, done? But you have done the significant reduction of significant figures part correctly. Just there might be some glitches in your calculation. Rest part is fine. Is it okay? Can you hear me? Okay, guys. I guess she's low somewhere. Okay. Now we will start with the errors in measurements. Errors in measurements. So we are done with this significant figures part, and we are also done with the dimension analysis part. So this is the last leg of our chapter, which is units, errors, and measurements. Right. So we will discuss about errors and measurements. So you have to read from your book what are different types of errors. I'll explain it briefly. Yeah, that is why there is different. They have written some short nice stories. You can write. You can read on your own. But first of all, let us understand what are errors. So, name of the topic is errors in measurement. Where I feel so embarrassed now by writing on this because my writing is so bad on this, and my writing is extremely good on the whiteboard, which I write in my class. But I guess it is you can manage to understand, right? Okay. Then, but so let us see what are the errors. What how do we calculate errors? Errors is defined as, sometimes they may also ask a definition, that is difference between measured value and the true value. Difference between measured value and true value. Yeah. See, your measured value can be less than the true value, or it may be more than the true value, right? But the difference between these two will give you the error. So error may be positive or negative, but generally we take the magnitude of the error. Yeah. So difference between the measured value and the true value of a physical quantity is called the error in measurement. Yeah. Now, what are different reasons for error? What are different reasons for error? Okay. So firstly, a part is your systematic error. This all is written in your book. What are systematic errors? Systematic errors can be of three types. First is systematic error. Say it is any shortcoming of your measuring method. Shortcoming means any limitation of your. You can write limitation of your measuring method. Limitation of measuring method. Yeah. Limitation, or we can say shortcoming. Yeah. Shortcoming or limitation of your measuring method. Second reason might be imperfection of the theory. That is, whatever theory you are implying on your experiment, that imperfection of theory. Imperfection of theory. That is, whatever theory you are applying to conduct your experiment, there may be some imperfection in that. Due to that, you may also encounter some error. Then third is it is due to lack of accuracy of the formula. Yeah, lack of accuracy of the formula. Guys, you might have seen, but not yet. But like you will see in the coming chapters that, for example, some scientists derived some formula, right? Then some other scientists did some corrections in that formula. You might have heard about that, right? So because that formula, first of all, that formula was not actually correct, or the accuracy was less, so due to that also you may have some errors, right? Generally, for example, we take a lot of assumptions while deriving certain formulas in physics, because we ideally assume a lot of things, right? So that is also some lack of accuracy of the formula used, right? Formula used for calculation. So these may be the three cases for your, broadly we can divide our systematic errors into these three possible cases. One is your limitation of or shortcoming of measuring method. What is, let us take some example of this shortcoming of measuring methods. For example, you are measuring the weight of a body in a weighing balance. Have you seen in lab there are some weighing balance in which they are closed in the glass chamber, right? Why do we close them in the glass chamber? So that the external air, for example, a fan is running in the classroom or in the lab, right? So the air pressure of that fan does not affect the weight if we have to measure really less quantities. For example, in chemistry experiments, we take very less quantities of each and every ingredient, right? So we cannot mess with the quantities of these. So we have to be very accurate. In that case, we measure that weight in the pan balance. We say that pan balance also, which in this balance measuring device is stored in a glass chamber. Now, what happens? Though you are according to you, you are doing perfect. That is, you are measuring very correct value. But this glass chamber in which you are measuring the weight, you might forget to take the buoyant force of the air, though it will be very less, but still it exists, right? So since you are not taking the buoyant force of the air, which will reduce the weight of the object, so that is called the shortcoming of the measuring method. Since you are not taking, or it may be it may be the limitation, it may be the shortcoming, right? So in your measuring method, you are not considering the buoyant force of the air, so that is also a kind of systematic error. Imperfection of theory. You have assumed so many assumptions that in your theory while deriving a formula, so that is also imperfection of theory. Lack of accuracy of formula used for calculation, that I already told you. Understood? All these three? Okay. Now, what are the second type of error? Second type of error is say this is instrumental error. Instrumental error. For example, when we have our practical exams in government schools, that will be a nightmare to conduct our practical exams in government schools, because in government schools always the instruments are faulty instruments, right? So we will never get our readings accurate. So instrumental errors are due to, it may be due to faulty design of the instrument. Some of the, like for example, you will see in engineering that we prefer to order our instruments for experiments from very distinguished companies, not for any desi companies. Why? Because sometimes the designs are faulty, so we may get some error in the experiment, right? So it may be due to faulty design, or you may not say faulty design, but you can also call it as imperfection of the design. That is, design is not perfect, right? So that is faulty design or imperfect design. Or this may also be due to inaccurate manufacturing. For example, there are some manufacturing defects, so these are inaccurate manufacturing, right? So due to some manufacturing defect, there may also be error which we encounter. So this will be put in the instrumental errors. Is it clear? Instrumental errors, all of you? Okay, then let us see the C part. C part, rest of all the errors are put in random errors. That is error due to any random things. It can be due to 10 number of things. For example, you are measuring, say you are doing some experiment in which you need to measure time as for time. For example, you have to see the time period of 30 seconds for certain experiment, but by the watch by which you are measuring that time period, that may be affected by some magnetic material present in the vicinity of that watch, right? So that is a kind of random error. Means it may be due to anything. It may be due to say flow in your eyes. It may be due to flow in your attention or focus, right? It may be due to anything. Any other apart from these two that we have already talked about, instrumental and systematic error, any other is counted in the random error. Any confusion? Okay, let me see. Acha, imperfection of theory. Imperfection of theory, beta, if there is any imperfection in theory, that is the theory you are applying. For example, you are doing some experiment in your lab, right? First of all, you might have noted in your practical notebooks that how will you proceed with the experiment. You write the aim, then you write the instruments, then you write theory. Now the method or the theory which you are implying on that, right? That theory may be faulty. For example, like in your 12th class, you will do some experiments with the concave mirror and the convex mirror, right? You will measure the distance of the object or distance of the image. You have already read about that in your 10th class. You will be doing some experiments in your 12th class. Now, you will assume some theory. That is, if I place this at this position and if I displace it from this position, then I shall displace my lens from this position uh, away from the object or towards object. That is your theory to, or your approach to conduct that experiment. So there may be some imperfection in that experiment. For example, you are measuring, you want to keep these three objects, your screen, your mirror and your object, in the same line, right? Their center should be in the same line. Now you are measuring with you are watching with your eye that they should be in the same line. And if by measuring with your eye, if these are in same line, then you will say, okay, this is perfect. But you may also encounter some parallax. We said parallax, that is parallax error. They may not be in the same line, but according to your eye, it is in the same line. So you are assuming by your theory that this is how you will approach, but that may contain some error. So that is how we call it some theoretical error. Yeah. Or sometimes we assume lot of theories to derive some derivation or for some formula. We assume some assumptions. So that assumption may also encounter some error. Yeah. So that is imperfection of theory. it also includes the personal error as well. Personal errors, that is errors by your eye, that is the personal error, or you're not focused. There is no this sharp line classification between that. Every other error is put in our random error. Random error may also include personal error. Yeah. Okay. Then, okay, guys. So in the next class, we will start with the how do we calculate error. This is just a theoretical part, which is not much of our concern, that you may read in your book also. Next class, we will discuss how do we calculate. How do we calculate these errors? Like, for example, absolute error, mean error, percentage error, relative error. Then in different formulas, how do we add? For example, if there is addition, if there is subtraction, if there is multiplication, if there is division of different quantities, then how do we calculate error in that? So in the next class, we will be learning about that. Then we will start with motion in one plane. Okay. Though, see, if I would have been given time, then my flow would have been different. For example, I would have after vectors, I would have go with basic mathematics like differentiation integration, which we will require in our physics to derive some formulas and solve kinematics. But since not a problem, we have discussed this first in kinematics. First once we complete our first chapter, then we will go with our IIT JEE flow, that is basic mathematics. Then we will connect that basic mathematics with the kinematics and solve some advanced problems on that. Okay, so keep reading from your book. I have Pradeep book. So if you have any doubt on any page, you can just tell me the page number and ask me the doubt. You can do that. Okay. So we'll see you next class. Yeah. Thank you all. Rohini beta, you missed some part. You can complete from the video. Okay. Fine. Okay then. Take care.